First, a short story. A number of years ago, I had parked on a small hill and a slight rise. And I tried pushing the car out of the swale and had a really hard time of it. And was kicking stones behind the tire, and it just was going really slowly. So I tried moving around to the front of the car and pulling it. I pulled the car maybe 20 feet over the lip of the rise in a few moments and was able to kickstart the car and go on. The basic notion of pushing versus pulling, I thought, might be relevant to my research, and I'll get back to that at the end of the talk. Oops. Over the last 6 years, I've been rediscovering and developing the use of diffusers to increase culvert capacity. A literature review that I conducted indicated that earlier research by Giovanni Venturi from 1797 and David Yarnell, published in 1926, demonstrated the increased capacity with diffusers. As part of my research, a field prototype here was constructed and installed at a site in Thorndike, Maine. An important part of the research required a method of accurately measuring the flow. To accomplish this, I developed the drawdown technique at the Thorndike Research Culvert and have subsequently used this at a site in Mattawamkeag, Maine. Whoops. The inspiration, for the drawdown technique came from an overactive beaver. He was determined to plug the culvert, and I was determined to keep it clear. The repeated drop in the water level when the pipe was cleared was recorded on level loggers that I had installed as part of the research. The resulting data shown in this slide show a storm peak followed by 3 drawdowns from the unplugging the beaver debris. I thought if I could reproduce a method of plugging the culvert like the beavers had, I could produce a drawdown, and that would give me insight on the capacity of the system. A mooring ball at the end of the culvert proved to be an effective method of plugging the culvert inlet. And in combination with a chain and come along, I was able to hold the mooring ball in place while the pond filled, in this case up to 5 feet of head, and release it from a safe distance at a selected time. And also do this on a time of my choosing rather than during a storm event. This is just after I had pulled the mooring ball, the flows starting through the Thorndike Research Culvert. And it also gave me an opportunity to look at the diffuser and monitor its performance during the high flow and make any adjustments that I needed. The drawdown curve for the Mattawamkeag and the Thorndike sites are shown here. The Mattawamkeag site on the left is a pipe system that was pre-tested before the diffuser installation completed a few weeks ago in early August. The Thorndike drawdown is shown on the right. The second higher peak was created by releasing water from an upper beaver dam that had ponded water. In both graphs, the rising limb of the curve represents the natural inflow. So that's a way of measuring the flow at the time of the experiment. And the steeply falling limb of the curve at the right represents the drop in the water level or the flow out of the system, with a caveat. You have to include both the drop and the inflow in the measurements. And that's sort of addressed here. By measuring the instantaneous rate of change of the water surface elevation at a specific stage and determining the water surface area at that stage, the instantaneous flow rate can be calculated for that head. As mentioned before, the stages can be determined by both a staff gauge and level loggers. The water surface area at various elevations can be determined by survey methods or LiDAR data where it is available. If there were no inflow, the outflow Q would be equal to the instantaneous change in elevation multiplied by the surface area. However, water flowing into the inlet pool slows the drop in the elevation of the pool. Therefore, at a given stage, the measured change in elevation during the inflow must be added to the measured change in elevation during the drawdown to determine the total change for the calculation of Q. So Q is the Q inflow plus the Q drawdown, or the area times the absolute values of the change in head from the inflow and the drawdown. And the mean pipe velocity is that flow divided by the area of the pipe, or for the diffuser outlet, that flow divided by the outlet area. During a drawdown at the Thorndike site, a mean velocity of 7.6 feet per second was calculated for the diffuser outlet. This compares favorably with the velocities taken during the storm event using a Marsh-McBurney FlowMate velocity meter. By computing the instantaneous flow rate for a number of water levels during a drawdown, the system's performance can be approximated to a good extent. The drawdown data falls in the range around the curve created by HY8 program for a similar pipe geometry. This was the pipe I pre-tested. And the surface areas I'm still refining, so it's somewhat approximate, which leads to the scatter. Accurate measurement of the inlet ponded surface area is still, at each stage, is very important for the flow calculations. LiDAR provides a method of accurately measuring the inlet pool area at various elevations. Accurate measurement of the rate of change of the water surface area is also, or water surface elevation is also essential. Smaller areas require shorter sampling intervals. For example, the Mattawamkeag site, I required a 1 second interval, where a 1 minute interval was adequate for the Thorndike site. Adequate inflow into the inlet pool is also important. And I found spring flows typically sufficient, and that's what I use for these two sites. I also did some work at the University of Maine hydraulics lab and using their flume. visible in this slide are the manometer board. I used 2 yards or meter sticks to measure the inlet and outlet pool depths. And the blue inlet, flared inlet and diffuser outlet were slipped onto the pipe ends. So I could test 4 systems with this setup. A straight pipe, a flared inlet pipe, straight projecting inlet diffuser outlet, and a flared inlet diffuser outlet. This slide shows a graph of the pressure through the pipe for a projecting inlet and a flared inlet. You can see there's a slight drop in the inlet pool water level with the flared inlet, but otherwise the data, the pressure data is quite comparable for both the flared inlet and the projecting inlet pipes. To that graph, I added the diffuser outlet with both a projecting inlet and a flared inlet. The first, you can see that the inlet water pool level drops quite noticeably, and also the pressure in the pipe drops quite noticeably. This is what hydropower industry calls recovered head, and is a feature, a characteristic feature of diffuser outlets. Also note that in all 4 cases, the outlet pool water level stays constant. And that's due to the weir at the downstream end of the flume. This slide presents a dimensionless performance comparison of a number of pipe systems. At the right are the data from the 4 pipe systems tested at the University of Maine. They were 1-inch diameter pipes. The 3 purple data points are the Thorndike diffuser measurements. And the 3 light blue are data from David Yarnell's 1920s research on diffuser. Looking at the data from the University of Maine, the red straight projecting inlet pipe was by far the least efficient. Adding a flared inlet, which is the yellow, was slightly more efficient, and taking the inlet off and adding a diffuser, which is the green, was a significant improvement on the flared inlet. And the blue is the flared inlet and diffuser outlet, and it was by far the most efficient of the 4 systems. These were all constant flow rate tests. And in looking at things, I found that a Venturi meter, which is a well-known method for measuring flow rates, and equates the inlet head, H1 in this figure, and the inlet to the diffuser pressure, H2 in this figure, with the difference with the velocity head of the system. And the coefficient CD in this equation is typically 0.98 for Venturi meters. For the diffuser systems, for Yarnell's diffuser, it was 0.837. And for the University of Maine research diffuser, it was about 0.82. So in conclusion, the drawdown technique, the method for measuring the instantaneous change in the water surface elevation and water surface area over a range of inlet water depths, allows the performance of the culvert or diffuser system to be measured at a predetermined and safe time. Additionally, the known flow rates generated by the drawdown technique can be used to conduct experiments along the downstream channel. The University of Maine lab results and analysis of David Yarnell's Iowa data indicate diffusers could be used like a Venturi meter as an accurate method of measuring flow through the culvert. The vacuum generated at the diffuser inlet represents the recovered head and is an effective method for pulling the water through the culvert, much like pulling my car was an effective method for moving my car over the slight rise. Thanks. I'd like to thank Maine Department of Transportation and especially Dale Peabody, head of research, and Charlie Hebson, my supervisor and head of hydrology, and the Civil Engineering Department at the University of Maine at Orono for the use of their lab, hydraulics lab in Flume, and Federal Highways Turner Fairbanks lab, and especially Cornell Carini, who's been connected with this project over the last 6 years or so as support and encouragement. Thank you. Any questions?
Is the diffuser only applicable for culverts and outlet control?
Yes. And part of the thinking is to modify the inlet in a way that would force outlet control.
Any others?
Mike, do you have any design guidance for designing these diffusers?
Yes, and that was published in a report I completed in 2016. It's the TRID database has it listed. I can also supply a PDF copy if anyone's interested.
Any other questions?
Okay.
Thanks, Al.